Hello and welcome to C++ Weekly. I'm your host, Jason Turner. I'm available for code reviews, contracting, and on-site training. Now, the other week I did leave out part of that in my intro, and I got some comments about it. Yes, I am still available for all of those things and happy to have a conversation with anyone who's interested. Although, on-site training at the moment is definitely a thing that is kind of on hold. So that's fine though. I've got other contract work that I'm doing as well, plus a huge shout out and thanks to my patrons who really help make this possible to keep continuing going and allow me to invest in the hardware and software upgrades and that kind of thing that I need. So I'm going to do something that's a little bit different today. I haven't really done anything like this in a long time where I've actually written on a piece of paper that is before you here. And what I want to talk about today is the fact that computers, generally speaking, use 2's complement binary math. And I want to kind of give us an intro to binary math. My goal now is to do something with binary and then integers and then an episode about BCD because that's come up a couple times recently. And then an episode or two maybe about floating point, that kind of thing. Number representations on our computers that we kind of have to deal with one way or the other in C++. Now, usually the compiler does these things for us. We don't really have to worry about it, but there's things that we kind of need to know. So base 2 numbering system, and this is probably familiar to most of you, but if I've got something like, I'm going to just do a 4-bit number here, those are my 4 bits. The first position represents the value 1, the second position is 2, 4, and 8. So this number, if it is a 4-bit number and has all of these that are enabled, then we get 4 plus 8 is 12, plus 2 is 14, plus 1 equals 15. So our range is between 0 and 15. Now, this is an unsigned integer representation. If we wanted to do signed integers, now there's a few different ways that we can do this. We can designate that this highest order bit is a sign bit. And if we did that, then we would have something like the value, if this was a sign bit and we had 1, 1, 1, 1, now this becomes negative 4 plus 2 plus 1 is 7. And then this would become positive 7. So we end up basically losing a value here because we've got 2 different representations for 0. If I had this or I had this, then I've got negative 0 and I've got positive 0. And this will come up again when we start talking about floating point numbers. And I've done other episodes like what is negative 0 and that kind of thing in the past before. So, my handwriting, it's not perfect, but hopefully it'll be legible for all of this. So what we end up with, most computers doing, and to the point that in fact C++20 now officially states that signed integers are 2's complement. So 2's complement means that we take the complement of all the bits and then we add 1 to it to get the to invert whether it's negative or positive. So I'll explain. If I've got the value, let's say I've got the value 3. So this is equal to 3. If I want the negative value 3 in binary representation here, I complement the bits and then I add 1 to it. So 1, 1, 0, 1. This is equal to negative 3. So the full range of values that we would have here, so I'm going to illustrate this as a complement and this is a plus. The full range of values that we have here ends up being that, well, let's see, if I've got the value 1 and I want to make that negative, let's go ahead and do the complement and then we'll add 1 to it. and I get 1, 1, 1, 1. So this is kind of flipped inside out from using a sign bit. So this is now the value -1. So our range, -1, 0 is still equal to 0. And if we've got 0, 1, 1, 1, then this is equal to 7. So the lowest possible number that we can have, the most negative number, is 1, 0, 0, 0. And we've been counting backward. So let's go ahead and do our inversion again. So if we've got 0, 1, 1, 1, and then I'm going to add 1 to this, then I added 1 here, sorry. So I add 1, this becomes 0, and this is just like doing math and decimal, except your highest possible value is 1. So I add the 1 here, and then I carry that, I add the 1 here, and I carry that, and I end up with the value 1000, which means that our range is -8 here. So our possible range is -8 to 0 to +7 for a 4-bit signed integer. Now, when are you going to have 4-bit signed integers? Not very often, but it's at least something to give us something to like really hold on to here for something that's easy to represent, something that's easy to show examples for. We can't do this so easily with an 8-bit integer, for example. And this is the moment where I hope that my recording is really working very well. So we've added numbers. Now, we've only added 1. And let's go ahead and take the value. Let's take -2. So if we got -2, that's going to be 1, 1, 1, 0, because keeping in mind that we're kind of counting backward from here to here, then this is -2. And if I wanted to, say, add 6 to this, I would expect the value 4 to come out. So the value 6 is 0, 1, 1, 0. And I'm just going to do an addition to this. And this is why we use 2's complement numbers in computers, because they kind of just magically work. So I've got 0, and I do 1. 1 plus 1 is 0, carry the 1. So I've got 1, 1, 0 here. But I have an extra 1 to carry. I have an overflow that happened. But if I take this number, this is in fact 4. So I added 6 to -2, and I got 4. Now, I do have this overflow bit, and if I cared about that, that might matter, because the computer doesn't care. The computer's not doing signed integer arithmetic. It is just doing binary arithmetic. So the computer has no way of knowing if I intended this to be -2, or maybe I actually intended this to be 14. And if I intended this to be 14 and I intended this to be 6, then what I end up with is this value here now. This is going to be the 16th 16 value bit. This would end up being 16 plus, and this would be 8, this would be 4, this would be 0, 0, okay. And I end up with 20. So like I said, it just kind of magically works. If I thought that this was signed numbers, then I get, if I thought it was signed numbers, then I get the 4 as expected. If I thought that it was unsigned numbers, then I get the 20 as expected once I take into account the overflow bit. It's just there. So, I mean, it's like really cool, actually. And so if we want to subtract two numbers, and again, we don't care if these are signed or unsigned integer representations. The computer doesn't care. It's just carrying out the same operations no matter what. Let's see, if I want to do -3, I guess. That should be -3. And let's just double check that. So if I negate it, then I get this, and if I add 1 to it, then I get, and that in fact does equal 3. So we can always double check that. So if I've got -3, and I want to, say, subtract another value from here. I want to subtract, I don't know, 5. So 5 is 0, 4, 0, 1. Oops, sorry. So that's the 4th place, that's the 1. Okay, that's 5. So if I subtract -3 minus 5, I'm going to expect the value -8. That is my expected value here. So how am I going to do subtraction? Well, I'm just going to do a 2's complement, a negation of the bottom value, and then add 1 to it. So now I've got 1, 1, 0, 1, the same value that we expected up on top. And then the 2's complement, I'm just going to make this a -5 to make it a subtraction here. And that's going to be our 1, 0, 1, 1. So I, again, negated this and then added 1 to it. And now I can do addition. So the CPU is often just doing addition all over the place for us. So I can add these, 1, 0, 1, carry, 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 carry. Okay. And then I end up with this overflow again. Now, this value, -8, is in fact this -8 that we expected it would be over here. So I did in fact get -8. Or again, if these had been actually unsigned integers, then it all would have worked out again once I took into account the overflow bit. So again, kind of works like magic. It's pretty cool. It's handy that our CPUs work this way. So there's then a couple of other things that we need to take into account. So if I wanted to do something like a bit shift left, so if I've got 0, 1, 0, 1, and this is my +5. Now a shift left, which can be represented like this in our C and C++ family of languages, left shift of left, oh my goodness, represented like this, left shift of the value by 1, is also a multiply by 2. So if this thing equals 5 and I multiply it by 2, then the result is 10. Now we know that that is outside of the range of possible values because we only have +7 to -8 here in our 4-bit number. I do this left shift by 1, I'm going to get 1, 0, 1, 0. So our interpretation of these values very much matters. This is in fact going to be equal to 10. And now why is the left shift by 1 equivalent to the multiply by 2? The same reason why if we had the value 1, 2, 3, 4 in decimal, and we did a left shift of 1 of this, not 1 bit in this case, but we're shifting by 1's place over, I get 1, 2, 3, 4, 0. So this ends up being a times 10 because that is the base that we're using is 10. In this case, we're in base 2. And so a left shift by 1, this now is equivalent to a times 2. Okay. So, but we have a problem. We have a problem with interpretation of these values because now we've just done something very unintended. If we were looking at this as a signed integer and we had done this left shift, then we end up with, what would this value be? That's 0, 1, 0, 1, plus 1 again. And we end up with this, which is equal to -6. So it depends on how we look at these values. Is this a positive, signed integer or an unsigned integer? But 2's complement, again, it kind of just works like magic in the compiler and the CPU, and it does what it needs to do, except in the case of shift right. So if I've got this intentionally negative value here, and I want to shift this right by 1. Now, most CPUs actually have something like an LSL, like a logical shift right, versus an ASL, an arithmetic. Scratch that. Most CPUs have both a logical shift right and a arithmetic shift right. So sorry about this mistake down here, but I'm doing a shift right because if I do a logical shift right, then I'm going to end up with something like this. And if I'm doing that's my logical shift right. If I'm doing an arithmetic shift right, and this is a signed number, then it's going to automatically pull in this sign bit here. So let's go ahead and consider again what this number is. The 1010 number, if we do R2's complement math, is 6, and we've probably got that math somewhere. In fact, we do. We have it right here. So that is 6. So this is -6. If I do a arithmetic shift right by 1, then I'm going to expect -3. And if I do a logical shift right by 1, then I'm going to take this number that is 10 and expect it to be 5. And in fact, it is 5 here. So I need to do the right thing. And this arithmetic shift right now is going to give me the value 1101. That's taking this value and shifting it right 1 with a arithmetic shift right. So that has propagated the sign bit over, and in propagating the sign bit over, I now get the value, if I do my 2's complement, 0, 0, 1, 1. So this, in fact, is -3. So hopefully that makes some sense. Got a little sidetracked here on the logical shift right versus arithmetic shift right and left. So this all pretty much works as magic, and it continues to do so when we start to talk about multiplication. And this is approximately where I'm going to wrap this up. So we're going to go ahead and multiply out two negative values and see what happens. If I'm going to take -3 and -2, and -3 is the value, it's always easiest, I feel like, to look at it from a positive value representation and then convert it. That's -3, and our -2 is going to be that. So I can do long multiplication here, just like I could do if I was doing decimal multiplication. 0, 0, 0, 0. I'm just taking the top number, multiplying it by 0, and then doing a shift left by 1 and multiplying by 1, and then multiplying by 1 again, and multiplying by 1 again. Now we know that -3 times -2 is in fact going to be the value 6. So let's keep that in mind. And we're going to add this up, and I've got this. Now I'm working on a 4-bit system here. So is that 6? That is in fact 6 that I am looking at here. So again, the math just kind of magically works. We can multiply, divide, whatever we want to do. Pretty much the only thing we can't do is shift right. Add and subtract we can do simply by using 2's complement, binary math, and then everything just works out in the computer, and your CPU is never really concerned about whether or not it is doing signed or unsigned, except in a few very rare cases, which is one thing that kept the logic so simple in earlier processors. So this, like I said, it's a little bit of an unusual video for C++ Weekly, but I hope that this made sense to you and gave you a little bit more of a foundation for how your computers work. and this has all been legible along the way. And we will discuss more about number representations in computers and coming up in future episodes. So thanks for watching this episode. Be sure to subscribe, hit the bell if you want to be notified about upcoming episodes.